Right, first of all, we're going to use the notation which I read as x bar to be the mean of a sample. If I call you collectively 13E, your group name 13E, if I wanted to estimate your mean height, I might just pick 3 of you. I might, for example, pick Chelsea, Corey and Rob. And if I average your heights, that would give me a sample mean. I haven't done everybody, I've just done a sample mean. However, if I had chosen different people, if I had chosen Greg, if I had chosen Siobhan, if I had chosen Sinead and Siobhan, and if I had chosen Billy, I would have got a different sample mean. So maybe I'll call that x1, x bar 1 and that x bar 2. And those sample means may not agree, even though they come from the same population. So overall there's a population of people, the population is everybody, and a sample is some of them. So x bar is going to be the mean of a sample, and I could have different samples. So we'll come back to that bit in a minute. Okay. The population, if we just make a note of what population is, a population is everybody, or if we're talking about leaves on a tree, every single leaf. There's a big tree over there outside the sixth form. If I want to know the average length of the leaves on the tree, I don't think anybody would actually go and measure every single leaf on there. If they did, and they worked out a mean, then they would know the population mean. The population mean, which we denote by mu, that has to involve every piece of data being measured. So we must have every piece of data included. We wouldn't often do that. So that's why we usually use sample means instead. You will come across lots of A-level stats questions where it tells you what the sample mean is and then asks you to do other things. And you think, well, if you've got the sample mean, if you've got the population mean, what's the point of doing anything else? It's just to make the questions doable at the moment. You'll see that later on. But going back up here, we said that the mean from Chelsea, Corey and Rob, and the mean from Greg, Siobhan, nice to see you this afternoon, Sinead and Billy, those means might be different. So x bar, the sample mean, it won't always have the same value, even if it's based on the same population. So x bar itself is actually a random variable. If it's any consolation, Sinead, I was looking at Kes for a minute, I just thought, I cannot think of his name at all, I've got to choose somebody else. And now it's suddenly come back to me. So, x bar itself is a random variable. It will be different depending on who's in the sample. Okay? What do you think the average x bar should be? If I took lots of different samples here, and then averaged those averages of the samples, what do you think the average sample average should be? X bar bar? Mu. Yeah, it should get close to mu, really. Okay. So in the long run, you would expect that x bar gets close to mu. What you expect to happen in the long run, can you think of any notation that might be useful or might sort of sum that up, what you expect to happen in the long run? Yeah. So in other words, the expected value of x bar is mu. That's correct.
So what's say after in the long run?
You would expect. Okay, you would expect. So we said x bar is a random variable. X bar can have different values depending on who's in the sample. X bar has an expected value of mu. If I did lots of samples, say it's the average height of people in here, say the average height of everybody in here, I don't know, 175 centimetres, 170 centimetres, something like that. There might be some samples where I just happen to pick the 3 shortest people in the group. There might be some samples where I happen to pick the 3 largest people in the group, but most of the time I would just get a representative sample of people in the group. If I drew a sort of frequency diagram showing that, say I know that actually the population mean for you lot of height is 170, and I may have weighed out the shortest person's 160, the biggest person's 180. What do you think my frequency diagram would look like if I worked out lots and lots and lots of samples? Like the normal distribution, it would look something like that, yes. You would get far more sample means here than you do out there. And somebody said it's like the normal distribution. It's actually true that x bar itself follows the normal distribution. We said it's a random variable. It follows the normal distribution. We've already said its expected value, in other words, its mean, is mu. We haven't said yet about what else goes in this bracket for the normal distribution. What else goes here for the normal distribution? The variance. Okay. What do you think would make our sample means become closer to the actual true population mean? We can only do things to our sample at the moment. A bigger sample. Yeah, so as the sample gets bigger, you would expect the spread of this to get smaller. The variance of x bar is sigma squared over n, where sigma squared there is the population variance, which you wouldn't normally know in practice, and n is the size of the sample. So as the sample size increases, the spread of these x bars, these sample means, decreases. And if you think about it, that makes sense. This thing here is fundamental to everything else we do in S2. Could you chuck a pen at me, please? Thank you. Thank you. Okay. This thing here is absolutely fundamental to everything we do from now on in S2, and that is called the central limit theorem. Okay, it's called the central limit theorem. It's fundamental to everything else we do. If you look in the textbook, there's a far greater detailed, thorough, precise where that came from than I've been talking to you for the last 9 minutes and 1 second. Okay? And if you want, it's a good idea to read through that in the book. It gives you exactly sort of where it comes from, and it puts more detail on it. But to be honest, if you don't get it, or you just think, it doesn't really matter as long as you know that and can use it. Okay?